Good morning everyone. This is G. Om Kedareshwara Kiran from Institute of Aeronautical Engineering, Department of Electrical and Electronic Engineering. Topic about Physics Tech Talk RLC lattice transfer functions. Introduction to RLC lattice. The RLC lattice is an electrical network composed of resistors R, inductors L, and capacitors C arranged in a repeated pattern. This circuit structure has unique properties that make it useful of various applications in electronics and single proposing. There are the symbols down represented below: resistance, resistors, inductance, and capacitance. These are the main three RLC points in RLC lattice. Definition of RLC lattice. An RLC lattice is a two-dimensional network of interconnected RLC elements, wherein individual components are arranged in a grid-like pattern. This configuration allows for the analysis of manipulation of electrical signals in a controlled and predictable manner. Here R1 equal to 30 ohms and L1 equal to 1 Henry, R2 equal to 20 ohms and C equal to 0.01 Faraday. Transfer function of RLC lattice. In this transfer function of RLC lattice, there are three dimensions. First one, frequency dependent. Second one, mathematical expression. Third one, complex behavior. That in coming to frequency dependent, we can see the RLC frequency. This transfer function of an RLC lattice is frequency dependent, allowing it to sensitively pass or reject specific frequency components of an input signal. Coming to the second one, mathematical expressions, the transfer function can be expressed as a ratio of polynomial in Lie space domain. With the numerator and denominator containing terms related to RLC component values. Complex behavior. The transfer function can be exhibit complex behavior such as resonance, bandpass, and bandstop characters based on the specific arrangement and RLC values and components. These are about the transfer functions of RLC lattice. Derivation of transfer function. First one is node analysis, second one mesh analysis, third one frequency domain. Coming to the node analysis, the transfer function is derived by applying node analysis techniques to the RLC lattice, which involves writing and solving a system of linear equations based on the circuit topology. Mesh analysis. Alternatively, the transfer function can be obtained by performing mesh analysis on RLC lattice, with focuses on the loop equations and the relationship between the current and voltages. Frequency domain. The derivation is typically done in the frequency domain, using the Laplace transform to obtain the transfer functions as a function of a complex frequency variable S. Characteristics of RLC lattice transfer function: resonance, bandpass, and bandstop pole zero structure are the three characteristics of RLC lattice transfer function. Coming to the resonance, the RLC lattice transfer function can exhibit resonance behavior where specific frequencies are amplified due to the interaction between the capacitive and inductive elements. Bandspace and bandstop. The bandspace and bandstop is a transfer function can also display bandspace and bandstop characteristic, allowing certain frequency bands stands to pass through while authenticating others. pole zero structure. The transfer function can be analyzed in terms of its pole and zero locations in the complex plane, which determine overall frequency response and stability of the system. Now coming to the applications of RLC lattice transfer function. There are four main applications of RLC lattice transfer function. First one is filtering. RLC lattice are commonly used as an active and passive filters of signal processing, allowing and selective filtering under unwanted frequency components. Impedance matching. The RLC lattice can be used to match the impedance of different circuit components, ensuring efficient power transfer and signal propagation. Oscillator design. RLC lattice can design and also the frequency selective element in the design of various types of oscillator, such as LC oscillators are called crystal oscillators. These are main three types of RLC lattice. Coming to the fourth type, which is none other than delay line. The distribution of nature of a RLC lattice can be exploited to create deals lines which are useful in timing and synchronization of applications. These are the main four applications of RLC lattice transfer function: filtering, impedance matching, oscillator design, delay lines. These applications are mainly useful in RLC lattice transfer functions. Without this, the RLC lattice transfer function may be analyzed and categorized in different forms. Now coming to the advantages and limitations. The advantages of RLC lattice transfer function is the RLC lattice offers flexible frequency response, scalability, and the ability of trailer the current circuit behavior to specify applications. Coming to the limitations, challenges include the complexity of analysis sensitive to component variations and potential for instability of certain configurations. So these are the advantages and limitations of RLC lattice transfer function. Conclusion and key takeaways. Versatile circuit. The RLC lattice is a versatile circuit. The RLC lattice circuit is structured with unique frequency-dependent characteristics, making it valuable in various electronic applications. Particle applications. Despite the analytic challenges, RLC lattice continue to find practical applications in areas such as filtering, impedance matching, and oscillator design. Coming to the versatile circuits, the RLC lattice frequency-dependent characters are of two types: complexity of requiring techniques and partial applications. These partial applications may or may not depend on analytic complexity. Despite analytic challenges of RLC lattice continue to find the particle applications in areas such as filtering, impedance matching, and oscillator design. These two are divided into three, coming second one as an analytical complexity. This analysis of RLC lattice of complex requiring advanced techniques in this complexity to derive the transfer function of the analytic complexity and understand the systems of behaviors. It need to be an complexity of various applications and versatile circuits of RLC lattice transfer function in the circuit structure to depend on characteristics of complexity. These are the main three conclusion key takeaways of the RLC lattice transfer functions. These may also vary from analytically complexable functions of RLC lattice transfer functions. Thank you.